does it work? Yeah.
Yeah, so about attacking searchable encryption systems.
Okay, so thanks for the introduction. Hi. So I'll be presenting the paper we wrote with my co-authors, Lefik Molvar, Melekonen. So I'm Cédric van Rompay. And in this talk, we're going to see privacy issues with some kind of searchable encryption. So about searchable encryption, even if we already saw about it, when you want to store data on a server that you do not trust, you can encrypt the data before sending it. So, but with traditional encryption, the server will not be able to do anything useful with this data. So the aim of searchable encryption protocols is to let you search this data. For instance, here you see a user asking if the data contains the keyword urgent and getting a response yes or no. And the protocol, of course, must maintain the privacy of the data, but also most of the time of the queries too. So in this talk, we'll mostly focus on this kind of simple search queries. So is this keyword contained in the document? So in this paper, we study the security of multi-user searchable encryption, or MUSE for short, that denotes searchable encryption with a large number of users that we split in two groups, the writers and the readers. So the writers upload encrypted data to the server, and they can choose which readers are allowed to search their data. What we found is that all the efficient existing MUSE schemes provide close to no privacy as soon as some users, even a very small number of them, collude with the server. So it makes the attack very powerful because with a very tiny collision between the server and a very small number of users, we'll see a very large violation of the privacy. The vulnerability is also extremely simple. So it leads us to wonder how it can still be present. So what we do is we show the seriousness of the attack, of the issue. We study the cause of the vulnerability, and we give ideas and tools to avoid this kind of issues in the design of future MUSE schemes. So the attack that we present is what we call a leakage abuse attack. So the term was coined by Cash et al. In their paper at CCS 15, and I'll often refer to this paper during the talk. A leakage abuse attack is an attack where the server combines some information that is naturally leaked by the searchable encryption scheme. That's called the leakage profile. And it's combined with some extra information that was obtained by some other means by the server. So there were many papers recently on leakage abuse attacks, but so far they have only been applied on single user searchable encryption. And so we applied them to multi-user searchable encryption, and it gave interesting results. So where does the vulnerability come from? Almost all MUSE schemes, so multi-user searchable encryption schemes, even if they are very different from one another, they are all based on a common structure that we call the iterative testing structure, illustrated here. So in this structure, what the server hosts are encrypted indexes. You can see 3 of them here that are lists of encrypted keywords. And the search operation consists in the server performing some tests against each keyword separately. Okay? So here you can see the test failing on the first 2 keywords and passing on the third. So this gives a lot of information to the server because encrypted keywords matching the same query, you can see that here that this reader sent one query to these 2 documents, and you have 2 keywords matching the queries. They must be the same keyword. We don't know what they are, but they must be the same keyword. And queries matching the same keyword, so the query of this and her query that match the same keyword must be the same query. So it allows a very simple leakage abuse attack in that if the server colludes with a user, so this one here, then the server has access to the content of all the indexes this user was allowed to search, had access to the documents in red, and there's nothing we can do about that. But because of these relations between keywords that the server could see thanks to iterative testing, the server will also recover keywords in other documents, so this one here. And this is clearly a violation of the privacy guarantees that we can expect from a Muse scheme. Because as a user, if I didn't authorize this user to search my document, I don't want my security to depend on his behavior. Otherwise, why having an authorization system at all? So the attack is very simple, right? But what's maybe less intuitive and more interesting is how powerful it is. To see that, we run statistical experiments. So we follow a methodology that's as close as possible to the one of CacheAL. Here we give some figures about the conditions, but the most important one is this. We have 30,000 emails, and we give the server access to only 20 of them. So they are the red documents here. So this is only 0.07% of the whole data set that we reveal to the server. And then we simulate just legitimate queries, about 1,000 queries per reader. And here are the results. By just doing its job of serving queries, the server is able to recover a lot of keywords. 90% of all the documents have at least 10% of their keywords recovered, and half of all documents have at least 30% of their keywords that are recovered. And query privacy is affected too in similar proportion. This is how the privacy of the data is affected. For query privacy, it's about the same thing. So we think that because no one did these experiments before, the power of this type of attack has been underestimated, and it's probably a first explanation to why the vulnerability is still present. So our attack applies to every Muse scheme that follows the iterative testing structure that are in red here. So as you can see, it's all of them, but one. But one in black, which is our scheme, by the way, previous publication. But this scheme is not scalable. It does not scale well to large data sets. So right now, in multi-user searchable encryption, you have the choice between a scheme that does not scale and schemes where you essentially lose all privacy as soon as just a very small fraction of the documents are revealed. So how is it possible that so many schemes are affected by such an attack? For all the papers that are in this box, the reason is pretty obvious. It's just not in their threat model. In these papers, the only threat that is considered is the server, and they never study what happens if the users behave badly. So what can we say about papers that don't include user-server collusion in their threat model? First, it's surprising, because in this kind of system, the users tend to be the weakest point in terms of security. Second, it doesn't really make sense, because when you are in a situation where you can trust the users, most of the time it means that you don't really need an authorization mechanism to make sure that users will not search the documents they're not supposed to see. And so in this case, probably you don't need a Muse system. Instead, you should use a symmetric or single user system that is much, much less costly. And what would be okay, actually, would be to have some violation of privacy when some users collude with the server, if only you had guarantees that a limited collusion would result in a limited violation. But our results show that this is not necessarily the case, so you need to show that on your system, and for that you need to study user-server collusion. So that's our first point. Do include user-server collusions in the security analysis of your systems. So now you see that there's one paper that's not in the box. It's multi-key searchable encryption by Rompay and Cédric. It's mostly known for being the protocol that is used in a framework called Mylar. So this paper was a move in the good direction because it is the first to consider users colluding with the server. But unfortunately, guess what? It used the iterative testing structure. And so it is affected by an attack, just like the others. So we proved this is the case by breaking the security of the Mylar framework. And if you're interested, the code for doing that is publicly available, and it also runs on my laptop. So point 2, do not use iterative testing structure. Sadly, we do not have an efficient alternative to this structure right now. So our point is that future work should focus on finding an alternative to that. Final point is on the misconception that the leakage induced by iterative testing structure is equivalent to something called leakage, called access pattern leakage. Here you can see that in the paper of Mylar, the system we attacked, the authors acknowledge that their scheme does not hide the access pattern. Now, all the state-of-the-art protocol in searchable encryption do leak the access pattern leakage. So it makes Mylar seem pretty secure. But we show that the leakage induced by iterative testing is much more dangerous than leaking no more than the access pattern. So it makes this statement a bit misleading. So access pattern in searchable encryption is the information about what document matches a given search query. So it's illustrated at the top. What the server sees with iterative testing is at the bottom. And it is stronger than access pattern leakage. So we call this leakage keyword access pattern leakage, or LKWAP for short. And we found several papers where the two types of leakage are considered as equivalent. So we give a formal definition of LKWAP, and we use our statistical simulation to show that it is indeed much different than access pattern leakage, that is named L1 in the classification of cache L. So here we can see the results of an attack against a scheme with a L1 profile and an equivalent attack against a scheme with the LQAP profile. And we can see that the attack is, the results are much better with the LQAP profile. So the LQAP profile is worse in terms of security. And we can see that on the other graph that LQAP is actually closer to another leakage profile named L3 by cache L, and that is much more dangerous in terms of security. So conclusion, you must include collusions in the security analysis of Muse. And when you do that with most existing Muse schemes, you see that security disappears. So we must find an alternative to the iterative testing structure. We must stop we don't need yet another scheme based on this structure. And no LKWAP is not equivalent to leaking the access pattern. Actually, so it's much worse in terms of security LKWAP than leakage access pattern. And actually, it would be already a nice improvement to have a Muse scheme that leaks no much more LKWAP. So at the end of the paper, we give some ideas that we're working on for improving the state of the art on Muse, but it's still a work in progress.